Hello, good morning, everybody. Thank you so much for joining. My name's Ilana Rennert. I help with outbound marketing here at SanDisk, and very excited to have Adam Roberts with us today, our Chief Solutions Architect at SanDisk, to share his knowledge and 5 tips for optimizing the data center. And but anytime during the presentation you have questions in the top left corner of your screen, please go ahead and submit them there, and we'll have some time at the end for Q&A. But with that said, I will pass it over to Adam.
All right, thanks for having me. So we're gonna talk about 5 tips for optimizing the data center, and these tips come from past history of helping customers to implement different solutions inside the data center, and the things that ended up being a hang-up, the things that kept us from getting as efficient as we should have been, and how we got around them. And a lot of them are food for thought as you're laying out plans for a data center. How do you gather the data you need to decide what you need to do and why? Why is always a big question. So let's jump right into this. There'll be some forward-looking comments made today. And, of course, I can't guarantee the future, but I'll give you my best guess as to where I think things are going and where they are now and how we got here. So, as I said, I'm Chief Solutions Architect for SanDisk Corporation. I'm also Director of Technical Marketing. I've been at SanDisk just shy of 2 years. Prior to that, I put in about 14 years or so at IBM. 10 years of that, more or less, was tied into the storage group, and about, we'll say, 7 years or so running the flash strategy for x86 as also part owner in the global strategy for IBM. And the past 1.5 to 2 years, somewhere in that range now, I've worked as the Chief Solutions Architect for SanDisk. So when we look at the data center, you've got to look at the data center as an ecosystem, a solution in and of itself. Too often we look at, depending on your point of view, when I was in server world, I tended to, at least early on, I tended to look at the server as the solution. And the storage guys who were providing drives tended to look at their solution was the drive. And they were very tied to the procurement specs of a specific device, but somewhere along the line, when you start building out large solutions, you realize it's not about the specs of an individual device, it's about the specs of the system, and you start looking at system specs and maneuvering things inside as to how to get there. It's truly a living, breathing ecosystem when you look at a data center. It's almost like a rainforest, so to speak. There's a butterfly effect. One thing can affect another in a way that's not necessarily transparent in the specs of the individual pieces. There are a lot of ways to build a solution. In small space, maybe you'll simply take storage and compute together in a single unit. You'll put this box on a shelf and you'll run your business. Maybe you have a mom and pop retail store, or even large chain stores may have individual servers running inside them, where you just have everything on a single server and you run it, and that's your ecosystem. You can actually keep things inside of a single server. In some cases, you'll cluster these things together and make a big virtual server where you got little pieces all being stacked together to create something large but still monolithic. What you're going to see more and more of as we move forward, you'll see resource pooling. Now, the idea here is if you really need to tie yourself to some specific infrastructure, instead of being a server and instead of tying yourself to cluster software, what will happen is you'll have storage and compute separate. And if you need resources in the compute space, you simply slice up another piece of the compute space. If you need more storage, you slice that off and you tie them together. There's a lot of work still to be done in this space. The NVMe over Fabric work that's going on in the standards body, if you ask yourself why NVMe over Fabric, well, it's because of resource pooling. And It's, as I said, it's a large scale, more hyperscale than anything, way of producing really large scale solutions that don't tie a user to specific pieces of hardware that have certain ratios that are locked down. And we'll probably touch a little bit on why that is and how that can hurt you or help you. Now, all these things, what do they have in common? Well, it doesn't matter the config. It changes one aspect of the solution that can really affect the final capability of the entire solution. It doesn't matter how fast your CPU is if the storage can't provide the data fast enough. It doesn't matter how fast the storage is if the CPU can't process the data. It's all about a balancing act. One thing going too fast may create a bottleneck somewhere else, but if the bottleneck can't be fixed, the wait states on that CPU or the wait states that's coming as a result of slow storage or vice versa, these things are cause inefficiencies, and we want to work around how do we get the best variables and the best results out of our variables, and how do we get this balance? Well, we're going to talk about some tips as to how to do that. And first, number one, absolutely above all else, understand your workload. What I see again and again, if you really want to balance your solution, and this is something that I encourage any customer I talk to dig into and look at very closely, because it's the biggest waster of resources inside of a data center, is actually understanding your workload. They think they understand their workload, but again and again, when they ask their IT guys, what's my workload, the IT guy, in a lot of instances, will give them a huge, huge margin of error to cover the fact that maybe they're covered, maybe they're not. So what happens is you don't want to build a solution based on wrong workload assumptions. This may be more often than not the amount of writes that they're doing. And these things can cause huge, huge problems with building extra margin in that you don't need. This can be write endurance. If you think about what's out in the field, when we started into the flash space, the number one thing that everyone was going for was SLC devices with 25 to 50 write fills per day. That was the bulk of the enterprise space. And if you look at the bulk of the enterprise space right now, the bulk of the workload is falling in one device fill per day. Now, it's not that workloads have changed from 50x to 1x. It's we understand the workloads more so than we did before. It's very seldom you're going to see people, even if you're doing this high-speed logging, where you're going to do 50 fills per day. And these things can create a need for more performance than you need. It can also create a need for more endurance than you need. So if you understand your workload, really look at the workload, you'll find that in most cases it's not as stringent as you think it is. And you can really save some money if you understand what your writes versus reads ratio is, what your average block size is, sequential versus random, the amount of writes you do in a given day. Really target these things as probably the most efficient key to building a data center, or even a single solution for that matter. So, tip two, very much tied to tip number one, understand the access density needed. Now, when you build a solution, as I said, you really don't want to just look at the specs of a single device, but you have to make certain these single devices don't trick you accidentally or lead you down a path where you just can't get what you need, or you got to do other things to accommodate for slowness, or you waste resources. So let's think about this. Access density, what is it? Well, think about it in terms of IOs per second per gigabyte. If you look at a 15K RPM hard drive, that's good for 300 IOs, and it's a 300 gigabyte hard drive. What this means is you're allowing performance access density of 1 IO per second per gigabyte on that device. Now, this is the slowest device on this list, and a lot of times we can use this as a meaningful tool, other times we can't, but understanding where it falls is very important. Sometimes we can get confused as we look at things like a 24 terabyte all-flash array. Now, an all-flash array, and these were based on some random pullings that I did at 70/30, just to give an idea. It can vary from one device to the next, but this is an example. So a 24 terabyte all-flash array with a million IOs at a 70-30 mix, small block random. You get a million IOs, you think, well, this is the fastest thing I can buy. Not necessarily. Now think about this. If you've got a million IOs, but you've got to spread those 1 million IOs out evenly amongst 24 terabytes of flash, what you're actually going to get for access density, performance per gigabyte used, is about 42 IOs per second per gigabyte. So that's much faster than a hard drive. But if you look at just the device specs, it's a very important thing that we really want to target here is don't just look at device specs. Look at how that device is going to be utilized amongst other players, customers that are going to draw from that device, how it's going to be used in infrastructure. And although this 24 terabyte all-flash array has the absolute largest individual number for performance, the access density is a modest 42 I/O per second per gigabyte. If you look at an 800 gig SAS drive, that's good for 100,000 IOs at that same 70-30 workload. You'll actually, if you work out the math, you'll see that it gets 125 I/O per second per gigabyte. So it's actually roughly 3x as fast access density-wise as a 24 terabyte all-flash array. And as you move into faster devices like a 1 terabyte PCIe card, good for 200,000 at that same workload, it's good for 200 IOs per second per gigabyte. So what you see here, there's a couple things that come out of this that's very useful as you start to build a solution. Whenever you build a solution, don't look at what people are doing. Look at why they're doing it. Otherwise, you're just following someone else. And the same with internally, if you're doing the same thing as last time with a couple new features. Always question what you're doing. So if you look at this, you can very easily understand why software-defined storage targets and things of this nature have become popular. Because if you deal with the simplicity of a SAS device or a PCIe device and you put it behind a layer of abstraction that is a server, you can design something that has better performance than, say, an all-flash array. And there's lots of reasons for it that we probably don't have time to cover, but one of the biggest ones is if you have a single point of failure, you've got to make that single point of failure so bulletproof that you end up losing some access density and you add cost. And these things play a role when you go with the larger all-flash array that you can get around. So the point I want to make there is understand why the pieces are used, how they enable things like software-defined storage, and which one you'd probably use depending on where you fall on this access density statement. Really understand and think about things in terms of access density. I don't hear enough people using the term. It really is important when you're deciding how much performance you want to get out of some piece of media. So performance margin of the SSD, they can allow for a really smooth RAID recovery. So let's think about this. How can access density come into play outside of the application? One of the mistakes that we can make very easily is to say, well, I need, let's say, 50,000 IOs. 50,000 IOs sounds fine. I've got a device that's good for 45. I'm covered. And you build your solution around that 45,000 IOs, and what happens? Well, everything's fine until something breaks. One of the things I found from my years and years in storage is everything works great until there's a problem. And 9 times out of 10, if you look at a RAID stack, if you look at any type of storage infrastructure, the most likely bugs that pop up, 98% of the time, turn up in the error correction tabs. That's where these things happen. That's where people are less likely to be spending their time when they're testing a device. They're testing it when it's running nice and pretty. Now, what happens is when you're running a RAID array, and this is probably a better example for HDDs versus SSDs. If you're running an HDD, one of the problems we have with limited number of drives inside of a server, as an example, one of the reasons software-defined storage is so focused on SSDs, you're limited to the number of devices in the box. And HDDs are so slow, we saw that 1 IO per second per gigabyte. What happens is, in a situation like that, what's going to happen, you're going to have a limited amount of performance that you can get. It just is what it is. And usually, because it's so expensive to add more for short stroking or small capacity, what you'll do is you'll simply get enough. Give yourself just a little bit of margin in case the workload grows or you're off in your measurements. Then you go about your business and you say it's good enough for my application. Then you have a drive go out in your RAID 5, and all of a sudden you're in a critical mode. And what does that mean? That means every piece of data that you try to get off that RAID array has to be recreated from a full stripe read, and you've got to create the data back from parity. This causes a huge amount of overhead. On top of that, the array is trying to rebuild with your hot spare or the drive you replaced that failed. And these large capacity arrays sometimes will take a week or two. And in that period of time, you're broken. You're essentially broken. Your application, where you thought, I'm fine, I had just enough performance for my application, you're actually broken for that week or two. It's really ugly. And if you look at, I think there's a 17% odds of failing a hard drive over the course of a year per the studies by some of the bigger hyperscales that have been done on like several million drives. You look at these numbers, that could mean, depending on how they're scattered out, half your storage at any given time could be in a degraded state. Now, you may say, I don't need the performance of an SSD, but that performance margin that the SSD allows you can be used by RAID controllers and devices of that nature to actually work on a rebuild while still providing the application's performance. So you may not need it for your application. Very important things to take into account as you're looking at access density. Don't just look at what your application needs. Look at what you're going to need in these corner cases, because nobody wants to be broken 20% of the time. It's really ugly. So tip number 3, hardware consolidation is your friend. We've reached a point right now where low-cost NAND devices coupled with these larger capacity points can allow for smaller solutions, smaller hardware footprints, least amount of power consumption. The whole solution costs less per gigabyte. And just as a side feature, you've got less points of failure and better performance. And think about this. On average, a lot of these solutions, literally 70 to 80 to 90, depending on the software, anywhere from 70 to up to close to 90%, we'll say 85%. Huge, huge numbers. These percentages, the cost of an overall solution ends up being software licensing. And if you're building software-defined storage and you can compress the hardware needed for that solution, if you can drop it by 5%, you've dropped it by you've trimmed almost that much off the cost of the solution because of the software licensing. What you've seen just recently with a number of large high-profile software packages going end of life, say, well, what difference does it make? Well, if you look closely, those software packages have gone, as you move to the newer ones, from a cost per socket on the license to a cost per core, which means the costs have gone up. So you'll literally, even after buying your hardware, 70, 80% or more of your overall solution cost ends up being these software licenses. And hardware consolidation helps greatly in this space. And we'll talk a little about how much. Now, this is an example of maximum amount of consolidation based on capacity, assuming that your enclosures can handle the workload and your workload is such that it'd be appropriate. If you look at, say, for instance, a SanDisk 3.84 terabyte capacity SSD versus a 300 gig 15K hard drive, I specifically targeted 15K because I'm assuming you're trying to get as much performance as possible out of spinning media. If you look at that ratio, 3.84 terabytes versus 300 gig, that's a 13.3 to 1 compression ratio. One of these drives can replace 13.3 of those. In this particular example I show here, I'm replacing 24 drive enclosures with 2 enclosures. So what happens is I manage to take 24 enclosures, I move everything down to 2, and 22 enclosures and the cables and all the infrastructure needed to support it and run it no longer have to be acquired. Now, based on some list pricing by one of our partners who are actually selling 15K drives, this is a server vendor actually selling 15K drives and a branded 3.84 terabyte drive solution, just based on list, and I know nobody pays list, but you can assume everyone gets roughly the same solution discount based off what they end up buying. So we got to start somewhere. So we'll start with list here. What I just described based on list is $481,000 purchase price versus $344. That's almost 30% lower cost to buy the SSD solution. Now, this particular example is as enclosures, but it could just as easily be a huge software-defined storage infrastructure where software running on these servers, you're paying per core, and you just removed 22 out of 24. You've basically done about a 93% hardware reduction in the solution. By doing this, in this particular example, you save the hardware, but in a software-defined solution with servers, you'd actually save the cost of the software licenses as well. Now, think about that. If you can remove 93% of the software license, and the software license accounts for 80% of your overall solution cost, you've just removed, we'll say, this is a rough figure, we'll say 70% of the overall solution cost just went away, and nothing was affected. Very, very powerful thing. Hardware consolidation is your friend. As I said, this particular example actually produces 110 terabytes of capacity versus 103 with the hard drives. So it costs almost 30% less and actually gives you 7 terabytes more. And depending on what you're building, could actually very well save you software licensing as well. And points of failure. 576 points of failure versus 48, plus each of those 22 enclosures that are gone is an additional point of failure. So if you wanted to sit down and do complex solution mean time between failure and DBS type calculations, you'll see a solution that's so much less likely to fail or have a failed component, one versus the other. Now, we just talked about the compression and consolidation of the data center. Well, this goes back to, as I said, it's not about the individual devices you're using. It's about the end results you get out of the solution that you built. So tip number 4, don't get lost in the components of the data center. Very, very important thing to consider here. What matters is the end result. You can do a complete reimagining of the data center. You don't have to build the same as last time. One of the problems I've seen as we move forward, you'll see this almost everywhere. When you, as an example, when you talk to architects that are looking at what's going to happen next year, the year after, as I just described, 15K drives versus a 3.84 terabyte drive, it's really easy for those who are trying to predict where the industry is going to say, oh, well, next year, 15K hard drives won't exist. Statements like that can be said. Now, on paper, if the entire world of 15K hard drives was me buying a server, that may very well be the case. But the reality is there's lots of people who are very comfortable with old technology. They're very comfortable with what they've done the same as last time. And as a result, it's real easy to just slip into doing the same as last time and add a couple of features. Now, the truth is, if you're willing to take the time to look into these tips and look into what we can do right now with SSDs, we've reached a point where we can do things that are so far out there compared to what we could do just a year ago that it takes time for the education to catch up. And also, if someone's in a 3-year rollout, they just started a 3-year rollout, something that's happening right now, they probably won't, in the middle of a rollout, change their hardware architecture. So these things cause things to take time. So just understand that. I could very easily say next year you'll never see another 15K hard drive, but that's not necessarily true. It's a question of who sees this first, who understands it first, and who actually takes advantage of some of the things we can do right now. So the bottom line is, the way I try to encourage people to look at this solution, look at solution cost and specifications. Now, what I just described earlier, I said, well, I can save you 93% of your hardware footprint. I can give you more capacity at almost 30% lower cost. So what's in there, if you're willing to look around you look around the fact that you're going to have to do some new things. You're going to have to look at what's capable of being done now versus before. I look at it as creating a Thevenin or Norton equivalent circuit. I like the analogy, having come from a background of design work and planar design. You know, the idea is Norton and Thevenin and Norton equivalent circuits. That's a voltage-based or a current-based modeling, where you take a very complex set of circuits and you boil them down to an input and an output, a voltage and a resistance and current. You boil it down to something much simpler than what's actually there. And the modeling allows you to say, all that matters is when I look at the big picture, when I make a Thevenin's equivalent circuit of my data center, is I've got 1 million IOs per second coming into it at 16K transfer size, mostly random, a little bit of sequential, and I need to hit X power envelope, and the output needs to be another 500,000 IOs or whatever it happens to be. You look at these numbers, and then you start looking at the other chips, the access density, the performance workload we just covered, the access density. What do you need? What devices will allow you when you pull from the media to get these numbers? And then you imagine from scratch, and you build something slightly different than you did before. So we just talked about the acquisition of the hardware. Well, what happens when you run it for a while? Very, very important. These are important, as I said, in the modeling of the data center. I just gave an example of 24 enclosures being compressed down to 2. Theoretical maximum based on capacity. Now, I've got a lot of data if anyone wants to see it on a later date. That'll take up more time than we have here today. But there's a lot of work that I've done with what happens if you can't do hypothetical maximum based on capacity. And you'll be surprised that it doesn't affect it that much. I actually have some charts where I quadruple the count from 2 to 8, and the number still stays at about 25% less cost to acquire. So if you have issues with access density per enclosure or device, you can actually still shrink quite a bit and still say instead of 2, compressing down to 2, we compress to 8. I can still do numbers that are pretty impressive. But what happens when you run this for a while? Now, I just described 110 terabyte solution versus I think it was 103 terabytes. What does this mean for somebody running it? And there's different audience members who are going to look at this different. Some will look at the acquisition, which I've just focused a lot on. Now let's talk about cost of ownership. Now cost of ownership, just some assumptions here. I'm assuming 16.8 cents per kilowatt hour, which I pulled some numbers from, I believe last year, and I pulled average power cost per state, and I got an average over states that were most likely to have IT in it. Hyperscale customers aren't going to pay 15.8 cents per kilowatt hour. Other people will. Some may pay a little more, some may pay a little less. So I'm just giving you an idea where the number comes from. I'm assuming 9 watts per HDD and about 7 watts per SSD and 100 watts per enclosure. Each enclosure for the fans and power supply inefficiencies in that enclosure, I'm assuming about 100 watts per enclosure. If you're building software-defined solution and it's built on a server, this number is going to be much, much higher than this. And the results I show here are going to be much, much, much more surprising, and the delta will be much larger. But I wanted to show the as friendly an example as I could towards existing infrastructure. And so I based it on 100 watts. Everyone here knows if you do a 2-socket solution, you'll pull 100 watts per CPU at this point. So we're talking more like 800 watts per enclosure. So just to give you an idea of how friendly I'm being with these numbers. I'm using 100 when if we do an FDS, it could be 800. So the HDD solution, as we described above with DAS enclosures, assuming this 9 watts and 100 watts and SSD at 7 watts, the HDD solution would use about $10,500 of power per year. That's 7,580 watts. Now, if you assume a 1.2x cooling factor, and depending on who you are, a big hyperscale customer may build their plant in Iceland so that they don't have to spend too much money on cooling, and they suck cool air in from outside. Another huge 2, 3, 4 square mile solution, maybe they just use gravity-fed water and they get it a little bit lower. But the average consumer isn't hyperscale, and they don't have that ability, and they're going to see something like 1 to 1.2x cooling factor. What that means is for every dollar you spend exhausting power out of a server or a storage device, you'll spend $1.20 removing that heat from the air and keeping things at a reasonable temperature. Heating and cooling, or heating from the device and the cooling that's needed to keep things at a reasonable temperature is very expensive. So that would jack this up to $16,676 and $20,000 per year. Now, the SSD solution is 536 watts. Very, very low power, and that's a $10,000 savings per year. And if you add the cooling factor based on 1.2x, if you feel like you use more than that or less than that, just be aware, because I don't want these numbers to just be pie in the sky and you don't know where they came from. If you feel like your ability to cool is less than that, you know, obviously if you cool at a 1x cooling factor, you can simply trim about 20% or so off of this delta. But right here at 1.2x, savings double to over $20,000 a year. In other words, you build this solution, you pay 30% less for it, but you end up walking away with $20,000 a year in your pocket on top of that. So these are things that are so far out there. I almost feel like the story we're telling is so powerful that, what's the word for it? It's almost too good to be true. You hear these things and you say, well, what are we going to do? Is that real? It's so huge, but the truth is, it is what it is. It's really powerful numbers, and that's why I want to give as much of the assumptions behind the number as possible, because this is so powerful. It's such an industry-changing direction we're going in here. I really want customers to understand how powerful it is, because it almost sounds like BS. You look at these numbers, you're like, how could that possibly be true? But the numbers are incredible, and the reason being, in this particular example, this is an HDD versus an SSD example. Silicon in idle state burns almost no power, and even when you pull data from the device, it's very little power to get that data from the device. And with an HDD platter, even when you're not pulling data, you're spinning a platter at 10 or 15,000 RPMs. So there's a lot of power burnt in mechanical movement of things. And as a result, and this ratio of cost versus capacity has really changed the nature of things quite a bit. So tip 5, you want to analyze and identify these changes to help you fill this solution in a more effective way. In other words, don't simply build the same as last time. It's very, very easy. I've done this myself. Sometimes it's important, depending on the amount of understanding you have of the infrastructure. You'll build the same as last time. One of the things I've heard from customers that really, really stands out to me is something that needs to be fixed. I'll ask a customer, what response time do you need in your solution? And what they'll tell me is, well, I need it to be as good as it was last time. If we can get it better, great. But I need it to be at least as good as what it is now. And what does that mean? That means they have no idea what would happen if their response time was a little bit less than it is now. The latency characteristics. They don't know. They don't understand it. So they build same as last time, and if they can get better, they'll get better. But as I said, if you go back to tips 1 and 2, understanding your workload and understanding your access density, and actually make effort to understand these things, it can help you here, and it'll free you so that you don't necessarily have to build the same as last time. Maybe you don't need a 10 fill per day device. You can use a 1 fill per day device as an example. When I was working in server land for IBM once upon a time, I had a customer come to me and ask me to help them analyze their workload. They were trying to decide if they needed a 25 write fill per day device, or if they could settle, if they could take a risk and go with a 10 fill per day device. Now keep in mind, this was at a time when an SLC device at 25 to 50 fill per day cost tens of thousands of dollars. And the 10 fill per day device was like 15% the cost. Things are a little different now. You don't even see much SLC now. But just to give an example of not understanding the situation they're in, when we were finished with the workload, they were actually doing about 1 fill per day. And they were looking at a 25 to 50 fill per day device. Now, by changing factors like that, by using the other tips in this list, You can look at tip number 5, and you can identify changes that will actually help you build your data center more efficiently. Don't build the same as last time. Ask yourself why you built what you built last time. And if it was built one way, simply because of some limitation that doesn't exist now, take this why into account. Question everything. Cost, capacity, the level of protection. Just as an example, a RAID 10 HDD solution. Why would someone use a RAID 10 HDD solution? Well, if you have a limited number of drives in a box, more than likely you're going to make a decision to go with the RAID 10. RAID 10 is very popular. And one of the reasons with HDDs it's very popular is because a customer will say, you know what, I'm going to give up capacity in order to get performance out of the hard drive. So a RAID 10 gets much better performance than a RAID 5 or a RAID 6. Although the RAID 5 and RAID 6 can give you better capacity. But there's such slow performance on an HDD, you may end up going with a RAID 10 just to get the most performance out of it. Now, as I said, question everything. When you move to new solutions and you look at new ways of doing things, let's look at this and say, what if I replace those RAID 10 HDDs with SSDs? Well, that may very well, the performance margin that I just gave you, may very well allow you to move back to a RAID 5. Maybe the RAID 5 wasn't feasible with HDDs because the HDDs were so slow. Now, if you've got some performance margin, maybe you can move back to a RAID 5. Now, what does that do for you? Well, if you're looking at an 8-drive array, if you build that with RAID 10, what are you going to get? You're going to get 50% overhead for your redundancy. If you do an 8-drive RAID 5, what's going to happen is you're only going to spend basically 12.5% of your capacity on redundancy. So if you can get performance margin out of a device, it's going to allow you to actually change your config. So always question why things were the way they were, why you're building what you're building, and you can go from a RAID 10 to a RAID 5, and not only do you get the performance you need, but you save the capacity as well. So you can have the best of both worlds. And these are the kinds of things that come into play. You can also do such things as maybe move from a RAID 6 to a RAID 5, simply because if you look at the specs of HDDs versus SSDs, the SSD, in most cases, will have at least 10x better uncorrectable bit error rate. So your chances of failing and losing a piece of data are much, much, much higher on an HDD than an SSD. And these things can allow you to make changes in your configuration that aren't necessarily obvious. Now, I kind of got ahead of myself a little with the RAID 10 and RAID 5, but because this slide would have been a better one to have up as we talked about this, but it's not through. So let's talk about these examples. Why would someone use a RAID 10? Almost always for performance sensitivity. You make a statement when you go with the RAID 10 that performance is more important than capacity. When you go with the RAID 5, you're making a statement that you feel that the capacity needs are more important than the performance needs of the RAID 10, or at the very least, RAID 5 is good enough for performance for you. When you go with the RAID 6, you're really trying to limit your exposure in critical mode. In other words, in a RAID 5, if you lose a drive, the week it takes to rebuild that large capacity array, you're exposed to a failure. And the uber rates of the drive versus the SSD, which I said is 10x, or in some cases 100x better for the SSD than the HDD. That entire time you're running and rebuilding that array, so you're hitting the array with full strike reads to recalculate the data that's lost as people are drawing off the array. You're also rebuilding the drive, you're hammering it, trying to rebuild it as fast as possible. And that entire time in RAID 5, you're at risk of an uncorrectable bit error. And the SSD, if you can get a 10 to 100x better, that may allow you to say, I don't need a RAID 6, I can go back to a RAID 5 because I'm 100x less likely to have this happen to me. Very, very important things to take into account that I think sometimes get overlooked. That's why this last bullet is a kind of a catch-all. Question everything. Ask why things are being done the way they are. Look at these things. Too often people will say, well, the Uber on the drive is 10 to the minus 16 or 10 to the minus 17. Great. If you jump to 10 to the minus 18, you just made a 10x improvement in that device with respect to failure. These things are really, really important and sometimes gets overlooked because it can actually affect, it's a butterfly effect in how the solution can be built when you look at these things like this. So, back to the points outside of changing the RAID config, we can simply change the design of the solution. Now, this particular slide, you can see here, so there's a data availability group on the left and one on the right. They look completely different. One of them, the one on the left, could very well have 13 enclosures hanging off of each of those servers. Or it could be some kind of control naming node controlling 13 servers. Either way, the idea here is on, let's say, the west coast of the U.S., there's a copy 1 and a copy 2 of the data, and on the east coast, there's a copy 3, copy 4. So you don't need to take backup. You've got plenty of copies. The west coast could fall in the ocean, or the east coast could be hit with a hurricane, and the other coast still has not only the data, but a redundant copy of the data. Or you could do the SSD solution on the right and build completely, as I said, up to 13 enclosures worth or 13 servers worth of drives pulled into the server or naming node or whatever the control node at the head, simply because of these large capacity points if you're dealing with small capacity HDDs. So actually be thinking about how to radically change the solution. Not just give me another feature, give me 5% better cost, 5% better performance. If you look at what we can do now, we can do some radical changes to the solution. Logically, the solution, like in this example, the solution still behaves very much the same, left to right. But physically, how they're built is radically, radically different, and it can change, as I said, software, licensing, the footprint needed, the power needed, all of these things come into play. So, in the case of software, we've talked about license cost and things of that nature, but, there's ways to actually take a solution and actually elongate the life of an old standard system. For instance, if you have a SAN, and this SAN is pretty much maxed out, but you want to increase your performance on the solution, you can add cache. And you can put, like as an example, SanDisk offers an application-based, host-based caching software. You can add this caching software and actually speed up back-end storage. But actually look at what's happening. What's actually happening. What's happening is not only have you sped up the solution, but you've had a profound effect on the back-end storage, which can make the back-end storage last longer, but it can also, when you create a solution from scratch, allow you to create it completely differently. So we talked about configs with RAID 5, RAID 6, RAID 10. Well, you may be forced in your SAN to run RAID 10 because you're trying to get the most performance out of it. But if you had 100,000 I.O. need out of a SAN, and you put flash inside the server as cache, and keep in mind this particular example, we're using inside the box DAS flash, and one of the reasons this example is written out this way is because earlier, as I described, we'll actually get the best access density out of these DAS type devices. But you could just as easily have an all-flash array box attached to that server in the cache. In this particular example, you can, if you're needing 100,000 IOs and you got, say, a 90% hit rate, what that means is 90,000 IOs per second out of that 100,000 IOs gets serviced by the flash that's being used as a cache. Now, that means everything's faster, but it also has a very profound effect on the back-end storage. The back-end storage is now only seeing 10,000 IOs per second, which can allow you to change the config of the back-end storage from a RAID 6 to a RAID 5 or a RAID 10 to a RAID 5. It can allow you to make changes like that simply because you're not hammering those devices as hard as you were, and you may be able to throttle down to maybe a more a less performance centric RAID 10 to a RAID 5 because you actually have some margin for the RAID 5 parity calculations. If you're designing from scratch, you may very well able to be to build a solution where you say, I don't need 15K drives. I can build with 10K drives because the bulk of my workload is being handled in the box. So you can fundamentally change the design of your solution. Don't look at it as just an acceleration play. You can actually change back-end storage design. I look at it as a back-end storage relief. You just took relief off of your hard drives, and as a result, your solution runs faster, but you can also use lesser components and save money. Now, just some other just general efficiency tips for the data center. These high growth areas where resources are needed per server, and I talked about this earlier, I alluded to it earlier in the first half of the discussion. If you're building things where you're going device per device, I want to touch on this slightly. Be looking at server disaggregation and resource pooling. The idea is if you're building lots of nodes and each of them run an instance of some application, and that application needs some certain ratio of CPUs and DRAM versus storage, and you build your server nodes, what's going to happen is there'll come a time where if that application changes and it needs a different ratio of CPU versus storage versus DRAM, you may get to a point where you can't use that node anymore because the ratio isn't correct. You can't put enough CPU horsepower and you can't get enough storage in it. Resource pooling allows you to simply add resources to your CPU pool or add resources to your storage pool. There's other examples where in a server, if the CPU is out of date but the storage isn't, well, then what do? You have to take the box apart and rip out the planar and add a new planar, or move the storage and SSD portions to another box. It becomes very ugly. You'll never have to do that in the case of resource pooling and disaggregation. Keep in mind that's usually done at a hyperscale level. It's something that's new. We're just tiptoeing into that. Some of the specs, such as NVMe over Fabric, are being designed specifically to allow really, really efficient connections between storage and CPU pools. And my slides were jumping around. My apologies. I'm not sure what happened. Questions to ask yourself. Do you understand why your current architecture is configured the way it is? Very, very important. Why are you using a RAID 10 or a RAID 5? Why are you using an all-flash array or a SAN? Why are you using these things? And get to the point of understanding why you're using them, because that will free you to make changes. You really need the current workload and access density needs. Have you built in the past lots and lots of margin because you didn't know better? And how are these things, or maybe it didn't matter. Access density, the number of writes you didn't matter on a hard drive. But if you're actually going to dabble in the space of SSD, you need to understand how many writes per day you're doing. Very important things. You know do you understand the amount of capital expenses tied to your redundancy and your oversubscribed hardware, like small capacity drives and short stroking? Ask yourself these questions. What it boils down is ask yourself, in general, you can almost boil this down to one bullet. Ask yourself why you're doing what you're doing. And as a result, that will allow you to, it will free you to create some new and interesting architectures. And I'm finished. Thank you very much. If you have questions, I'm at adam.roberts@sandisk.com.
That's great, Adam. We actually do have quite a number of questions that came through. So we'll start it off. How does the PCIe bus limit the pooling resource access in microseconds?
How does it limit? Well, see, here's the thing. There's several different things that can be said about this. First off, there is a thought in the industry that running PCIe versus, say, SAS JBOD, the PCIe solution will have a better response time than the SAS connection. Right up front, I'll tell you that's not necessarily true. Marketing people who are trying to market a PCI card versus, say, a JBOD, a SAS, 12 gig SAS, or whatever solution, they will draw charts saying, look, there's more boxes in this path. There's the drive, there's the backplane, there's the JBOD controller. There's more boxes, so evidently the response time must be worse. Not necessarily true. I've done a lot of measurements in path lives where JBOD type connections versus PCIe were very, very similar. Now, I'm going to take the next step on that and say as we move into NVMe, that's not necessarily true anymore. What happens is as you move into NVMe space, you once again ask yourself, why does NVMe exist? A lot of people will say, oh, well, we're just standardizing. Well, NVMe is much more than just standardizing. The idea behind NVMe is we're trying to reduce the number of CPU cycles needed to move data from point A to point B. And it's an efficiency statement as much as anything else. Although it is a standardizing effort as well, one of the most important things is this efficiency. And that's why, as I described earlier, you'll see this in the world of fabric and resource disaggregation. The idea is you want to have the data moving from the CPU resources to the storage resources as limited as possible. And hopefully something in what I just said answered that question. The bottom line is NVMe with PCIe, as of right now, will be more efficient as far as response times on moving data from point A to point B. If you look at standard non-NVMe devices versus JBOD type solutions that don't have RAID, the numbers are very similar. Now, if you add in RAID in any of these, be very, very clear, if you add in RAID in any of these, the overwhelming response time effect is the calculations that are needed for the RAID, particularly if you're in a critical state, just so that's been said. And NVMe over Fabric is the solution for making response times, which are going to be very, very sensitive once you start separating the storage from the CPU DRAM resources in the scaled out architecture with resource disaggregation. The NVMe over Fabric is specifically being positioned as the standards roll out to try and tighten that up so that the response times are reasonable.
Gotcha. Another question we have, and I'll pull up the slide that they're referencing, but the question is, any performance issues accessing a memory mapped resource pool via 100 gig Ethernet fabric? And that was in response to, let me pull up the slide here, on this slide here. And I'll repeat the question for you, Adam. Any performance issues accessing a memory mapped resource pool via 100 gig Ethernet fabric?
I don't have measured numbers that I can share. I can't say, well, it's X number of microseconds, but this goes back to the NVMe over Fabric. NVMe over Fabric is going to exist to try and shorten that number. If you look at some of the stuff, if you look at last generation's IBM X5 box with, we basically had a memory extension box to extend the amount of memory that went into the 4-socket boxes. You know, you'll notice that wasn't built on Ethernet. If memory serves me, that was all InfiniBand. Ethernet has some limitations when it comes to trying to be memory mapped to anything. And nothing in this particular presentation do I touch on memory mapped, but I'm sure you're, at least some of the people on the phone will be aware of the load store stuff we're trying to do with resistive RAM. And we are looking in that direction. And for that to work efficiently, we'll need things like NVMe over Fabric to be well in place, just because, yeah, there will be some limitations if you don't have things like that in place.
Okay. Another question is, can you provide, well, I doubt you know the part number off the top of your head, but can you provide what SSD drives and specs that you were using for your examples?
Yes, the SSD drive was a 3.84 terabyte Optimus Max drive. And as used in the example, I used the Lenovo device. I could actually probably give you the part number. Given just a second, I might be able to give you the part number. I don't want to slow this down too much, but
yeah, no worries.
At the very least, understand I used list prices from Lenovo, and it's the Optimus Max 3.84 terabyte device.
Okay, and we can always follow up personally with that,
yeah.
the person that answered that question.
If you do an internet source on SanDisk 3.84 terabyte SAS, it'll come up. There's only one of them.
All right, another question for you, Adam. What kind of power supply do you need for an SSD drive? Is it the same as for HDD?
You'd use the same. You could actually, if you were designing specifically around SSDs, you could design for something less. When I owned a storage group in my past life, we would try and allocate about 11 watts per bay for hard drives. In general, in fairness to the hard drive, I usually pulled about 9 watts. It didn't really matter if they were reading or writing. The thing that's pulling all the power in a hard drive is the fact that they're spinning a bunch of platters at 10,000 RPMs. That's where the power is mostly being consumed. There's a little consumed by the head moving. In the case of an SSD, you'll find when an SSD isn't actually pulling data, it pulls almost no power. Now, the SSD described the 3.84 terabyte device. We're allotting about 7 watts at a 70-30 read-write mix and 9 watts for the HDD. So if you want to retrofit an SSD into a hard drive bay, it's going to use less power. And if you're designing from scratch, you could probably trim 15% off of the cost of your power supply simply because of what I just described. So it'll absolutely fit in the same environment. You can change it for efficiency reasons. If you want to use the power supply, for either or hard drives or SSDs, you just leave it the same. But what you'll find is the SSD always pulls less power than the HDD, unless you spill into like the PCIe space. Open a big can of worms even bringing that up. But there's some by 4 PCIe stuff out there, which is not necessarily the discussion you want to have, SAS versus SAS. When you throw by 4 PCIe in the front of the box, you open up the ability to do 25-watt devices in the front of the box, which, of course, is a much larger performance and power play. But in the SAS space, the SSD will always pull less.
And next question, and I'll pull up the associated slide. What is the MTF on these SSDs opposed to hard drives? And this was in regards to your slide on enclosure count.
So here's what you'll normally see, device MTBF versus device MTBF. You'll normally see about 1.5 million hours on an HDD for mean time between failure. And the SSDs will typically be 2 to 2.5 million hours mean time between failure. So, we're talking 45, 50% better MTBF, plus you reduce the part count from 576 down to 48. So not only are the parts considerably better MTBF device per device, but you actually have less points of failure. So if you were to work out a solution MTBF, you'd be working out a calculation. If you do mean time between failure on a device, it's basically a summation of the likelihood of any component in that device to fail. You'd say, well, the likelihood of a capacitor plus the likelihood of a VRM versus the likelihood of the connector versus the controller. You could add up and create a formula for how often this device is likely to fail. So you can do that with a solution. And as you do it with the solution, there's 2 aspects of it. One, the solution will have a better MTBF because you've simply removed so many points of failure, but also the devices themselves are 2.5 million versus 1.5 million.
Okay, thank you. Well, there are more questions that have been asked, but unfortunately we are out of time. But I do want to pull up the last slide, which anyone does have any specific questions for Adam, please do reach out. You can also tweet us at SanDisk Data Center CTR. We'd be happy to answer your questions there as well. But thank you everyone for attending. I will be posting the presentation on the attachments tab probably within the next 30 minutes, so check back in if you'd like to have those available. Other than that, have a great day and thanks again. Bye-bye.
Thanks.